Okay, then the next what we're gonna do is forecasting. Okay, so then let me explain the theoretical background first, and then we're gonna practice using the MATLAB. Okay, so here, what does it mean by forecasting? Okay, so then we have data up to time capital T, right? Okay, and then the y cap t plus 1 is of interest. Okay, so then this is a future value. Of course, it must be random variable, right? So then forecasting y cap t plus 1 means that the deriving the distribution, I would say posterior distribution of y cap t plus 1 given the data up to time cap t, right? So this y is the early observations available at time capital T, right? And then we wanna generate, or we wanna compute the posterior distribution of y, and then, or you can simply say that the expected value or a variance of y capital T plus 1, right? Okay, and that what you have to note is that here only y is given, data is given, whereas the primaries are not given. It means that we have to consider the primary uncertainty, right here. So this is the definition of the posterior predictive distribution. Okay, and then to derive or to figure out what kind of distribution this posterior predictive distribution is, you have to compute what? Posterior predictive density, right? And then this is posterior predictive density. And then this is just math, right? This can be derived from this joint density between y capital plus 1 beta and sigma square, right? And then here, this equation can be re-expressed using these two terms. Here, the y capital plus 1 given beta sigma square and y times the density of beta and sigma square given y, right? And what is this? How is this called? This is what? This is posterior distribution of the parameters, right? And what about this? Do you know the distribution of y capital plus 1 given beta and sigma square? Yes, we know this. This is normal distribution, right? If beta and sigma square are given. What about this? Y capital plus 1 given y. Is this still normal? It's not normal, right? Let's go back to our model here. This model. Okay, where is it? Where is it? Okay, where is it? Yeah, it should be around, yes. Okay, yeah, this is our model here. If beta and sigma square are given, then y follows normal distribution. If beta and sigma square are not given, if they are unknown, then you have no idea what kind of distribution is, right? So the distribution of y is not standard error. It's standard only if beta and sigma square are given, right? Okay, here, okay, right. So then again, what's the distribution of y capital T plus 1 given the primaries and data? This is normal distribution, right? And we know the distribution of beta and sigma square. Or we have to say that we have the posterior samples for beta and sigma squares, right? So then according to this equation, the posterior distribution of y capital plus 1 can be generated by using this algorithm, right? So given the posterior samples for beta and sigma square, we can compute the conditional mean of y capital plus 1, right? Because x capital plus 1 is exogenous variable. This is given, okay? This is given at time capital because this is exogenous, right? And then we have the beta and sigma square, right? So then we have, from this normal distribution, we are going to generate a number of y cap t plus 1. Okay, for each posterior sample for beta and sigma square. Okay, how many samples do we have here in this example here? What's the MCMC size? MCMC size is what here? Okay, anyway, it's 10,000, right? 10,000. It means that we have 10,000 beta and sigma square, and for each pair of beta and sigma square, we can generate one y cap t plus 1. So that means we have also 10,000 samples for y cap t plus 1. Okay, then let's do this.